Hello, and welcome to today's Australian Water School webinar on optimizing your flood model for cloud computing. I'm your host, Cray Price, and I'm excited to introduce you today to a dream team of flood modelers who will guide you through today's topic. But before we get up in the clouds, let's get down on the ground and see where everyone's coming to us from today, from right around the world. Welcome to each and every one of you joining us live, and also to those who will be watching the recording at a later date. Now, let's welcome today's presenters. We've got Sophia, Chris, and Samantha. If you can turn on your cameras, let us know a little bit about yourselves. Sophia will be introducing a bit of an offer here at the end, so we're going to start with Chris. If y'all can just let us know where you're coming to us from today and how long you've been up in the cloud.
Thanks, Cray. I'm coming from Brisbane, Australia, on the East Coast. I have been hydraulic modelling for 20 years. Probably around about 5 or 6 of those have had exposure to cloud computing.
Excellent. And Sam, over to you. Where are you coming to us from this morning?
I'm also in sunny Brisbane, although not as sunny today as sometimes. And I've, like Chris, been modelling in hydraulic models for about 20 years, but the cloud, probably 4 to 5 years. Our team has been using Flood Platform starting in its internal forms before using the external form available now.
Excellent. Sophia, over to you, and let's hear an introduction of yourself, and then we'll hear a little bit of an offer for today's attendees.
Great. Hey, everyone. I'm coming from Tweed Heads, New South Wales in Australia. And about 7 years ago, decided I wanted to be moved from engineering to product management. So I had to do a bit of a crash course in web to get myself there. So I about 7 years in the cloud.
Excellent. And we see here on our screen a special offer if you wanted to mention that to the attendees today.
Yeah, so Flood Platform, as Sam mentioned, it's been available internally at Jacobs for a long time, but we've just released the external version finally after a year of waiting. So if you're interested in trialing it out, I've got a free 14-day trial that you can scan the code there or just check out our website and it'll go straight there. So as soon as you sign up, you get access.
Excellent. Well, thanks to Jacobs, our sponsor for today's webinar. What you may have noticed, if you've seen some of the previous webinars that Jacobs have been involved in and that Sophia has helped put together, there are some product-specific things that you might see in those webinars, but a lot of what's covered on these webinars is for the good of the industry as a whole, no matter what modeling platform you use. And we've got people representing all sorts of different software packages here today with you who will be guiding you through some of these processes that will help you no matter what kind of modeling you do and no matter what platform you might use. So if we can have a quick look at the poll results here, what we wanted to find out in the very beginning, how many of the attendees today have actually used cloud computing? And we're only at 20%. So I guess I would ask that question then around to the presenters today. Then Chris, does that surprise you?
Not really, actually. That's pretty on par with what I was expecting.
Okay.
Yeah, that's...
We'll see. We'll see if we, if we did another poll like this a year from now. We're hoping that by getting some of this information out there and by making this accessible to everyone, maybe this percentage goes up. And there will be cases, and we'll be fairly transparent with you. There are cases where it's not going to be worth getting up into the cloud, and we'll talk about the pros and cons that way. So what we'll do here, the way this is going to work, we're going to start out with a presentation that Sam's going to guide us through. So Sam, you could probably already start sharing your screen. And then what will happen is the rest of us will drop into the background and we'll, even though you won't see us on video, we'll be frantically typing away, answering your questions on the Q&A line. Some of those, again, those that are upvoted the most, will be covered live by our technical panel. So what we've, while one presenter is talking, the others will be answering your questions. And so we'll come on periodically and maybe ask you a couple of audience questions as well. So I can see your screen just fine there, Sam. So if you wanted to scroll down through where you had a couple of, I think, some initial poll questions that we're going to do, the way this will work, first, Sam's, actually, you can go back one more slide. I want to just let you know who's doing what. So if you fast forward, Sam's going to be doing the presentation about optimizing the number of scenarios, and we'll ask you quick question about how many scenarios you've done. Then Chris will talk about minimizing the simulation runtimes. And then Sophia's going to talk about utilizing the cloud to do mass simulations. So we'll have a Q&A at the end, but now let's get into the next question here, which will pop up into the poll. If you can go on to that next slide. you as the audience, this is interactive. So if you can get your answer in quickly, because we'll close this poll momentarily. What's the largest number of scenarios that you've modeled in a single project? So we've got a couple of different answers for you here. They're not necessarily in order of magnitude kind of thing. Sometimes you might have people getting many more than 1,000, or only one who might be less than 100. So if you can answer that question for us, we'll do a quick run around the room here and ask you the same question for the presenters while we're closing that poll up. Let's start then with Sam. What's the largest number that you've ever put into a single project?
It's probably too many than I want to count. I actually prefer not to think of the ones where it's lots. But I think one of them where I had about 800,000 simulations we needed to, but by using pragmatic tools and thinking about what our problem was, we only needed to run 100. So that's what I call success.
All right, Sophia, what was yours? What's your highest number you've gone with?
Look, I haven't been modeling for a long time. I think I got up to about 800 back in AR&R 87 days. But I've done a lot of testing in cloud, so we've run thousands of simulations in parallel.
Okay. And Chris, are there any caveats to this question that affect the number of runs that you've done?
How many errors I make when I'm building the model, perhaps?
That's a good one, yes.
So I don't want to count how many I've done over the whole project. Look, once I have established a nice model that I'll be doing for my design runs, there have been instances where I've done over 1,000, for sure.
Well, then you'll be up in that highest category. Let's have a look at the results now and see what the audience has come back with most for the number of scenarios. And this is with or without a cloud. This is just the number of scenarios that you've done for a single project. 70% is under 100. So very few have gotten up into the over 1,000 category. And in the chat line, so this will be not a technical question, but in the chat line, let's see if we can just keep a running tally, like a bid list here. If somebody has run 1 million, has anybody run 1 million simulations? If so, pop that into the chat line and let's see who gets the record there. So with that, the rest of us will drop into the background. Sam will take over with the presentation. I can see your screen just fine, and we'll come back with you when Chris gets into his presentation. So over to you, Sam.
Oh, thanks, Craig. I can't actually see those big numbers coming through the chat at the moment, but I'm sure there are some big ones.
We'll keep you posted if we see something come up at the end of the presentation. We'll do a little running tally and let you know.
But there were definitely some big numbers in the poll. So I guess let's explore some of those reasons behind why we end up doing so many TUFLOW simulations. Obviously, our aim in doing many simulations is to represent natural variability in flooding behavior now, in the past, and in the future. And AR&R gives us some guidance on how to do this, to consider rainfall frequency, rainfall duration, temporal and spatial patterns of rainfall, joint probability of tributaries and catchment conditions. And often we need to consider changing catchment or floodplain conditions as well as design options. And to cap it off, now we're thinking about climates in the future, and adding that to the mix. So when we, do the number of iterations, when we multiply all those potential variables together, that can end up in quite a lot of different scenarios. So what can we do to optimize the number of simulations that we're doing? We need to balance robust technical outcomes with manageable runtimes. I'd love to say there's a single, simple, silver bullet answer, but really, as many things we do, it comes down to engineering judgment and a thorough understanding of the objectives of our modeling. So what questions should we be asking ourselves in making that engineering judgment call on how many simulations is enough to answer our problem? Well, the first question, I think, is what is our project requirement? Are we in control of the number of simulations? And if we're not, can we influence it? And then I think the next, which is probably arguably the most important question, is what is the problem that we're actually wanting to use our flood model to answer? Is it a design problem? Is it a floodplain planning problem? Is it a dam break problem? All of those questions about what we're trying to solve will influence the answer to how many simulations we need. So is there a single purpose or multiple purposes? How complex are the problems that we're trying to solve? To be honest, the more complex our problem is, the more simulations we're more likely to need, or the more thinking we'll have to do to maintain the rigor in the answer if we're simplifying the number of scenarios. So some other questions we should be thinking about is how spatially varied is our problem? Is there a single point of interest, or do we need to consider multiple points of interest which might have different flood behavior? Or in fact, do we want to look at the entire floodplain? And then the last question is, what flood behavior are we interested in? If we're only interested in flood peak or a flood flow at one location, it can be very simple to reduce our hydraulic simulations. Whereas if duration or timing of flood arrival is of interest, well, we might need to move a little bit faster and work a little harder. So a couple of examples to get your creative juices going. Full 2D with ensembles has really become the default starting point for our industry following publication of A&R 2019. It's generally appropriate where we have multiple locations of interest, are interested in multiple measures of flood behavior, and it's typically required for design of transport infrastructure and catchment-wide flood studies. But what else can we do? On the simple end, we've got hydrologic simplification. That is the use of a hydrologic model to identify representative events for simulation in a hydraulic model. It's most appropriate where we've got one or a couple of points of interest, and it's only a single flood behavior that's of interest, such as peak flood, peak flow, or level. The full range of scenarios are then simulated in the hydrologic model, which is typically a lot faster and less prone to issues with running. And the event producing the critical flow or level at the location of interest is selected for simulation in the hydraulic model. I've used this recently on a concept design of a bridge duplication on a very small waterway. This approach can even be used more broadly when further development of the hydrologic model is undertaken to produce a hydraulically equivalent hydrology model. A hydrologic model that produces behavior matched to a hydraulic model or calibrated to the hydraulic model. This approach has been used by some of our councils in Southeast Queensland. So then we can add a little bit of additional complexity and, of course, model setup time. So we can develop a simplified or low-resolution hydraulic model as well as our detailed hydraulic model. This simplified model will run more quickly than the ultimate, more detailed model, but can be used in a similar way to what I described with the hydrologic simplification. A well-known example is the Brisbane River Catchment Flood Study. I think a 1D model was used to run thousands of scenarios, which then informed a Monte Carlo stochastic analysis. From this, a small subset of representative events were chosen for simulating in a detailed 30-metre grid resolution TUFLOW model for the entire catchment. I think the fast run times are around 4 minutes compared to the 16 to 32 hours for the detailed model. Chris, did you want to add anything on this one? I believe you were involved.
I should caveat, my colleagues were involved. I didn't actually do any of the modelling myself, but I think you've given it quite a good summary. There was essentially a lot of benefit in creating a surrogate model where the 1D could reproduce equivalent accuracy at different point locations. And those 11,000 1D simulations were used to inform the 60 that were selected in the 2D. And those 2D runs obviously took longer to run. So really innovative approach.
Thanks, Chris. And I guess the final current buzzword, using AI. So the use of AI or data science in flood modelling is becoming more accepted. Machine but learning-based models can be trained on a detailed hydraulic model to predict a range of flood behavior, again, reducing the number of hydraulic simulations in a detailed model. Improved results have been demonstrated by combining this approach with a low-resolution hydraulic model, similar to the previous example, where AI is used to convert low-res results to high-res results, significantly reducing the runtime. Shout out to my colleague Nils and Yurong for advancing this field with their research. Currently, AI methods are most applicable for flood depths across large areas where the number of scenarios required exceeds the capacity to run in a reasonable timeframe. A recent example for Jacobs was the Oxcam project in the UK, where 45,000 scenarios were simulated to inform a decision support tool. Sophia, did you want to add anything on that example?
Yeah, I think this is a really interesting one that I've shared with other people before, but I wasn't involved, just my team. But 45,000 simulations was a lot, but actually what they needed to do was they had 27 million combinations of options to upgrade the infrastructure to prevent flooding. And out of those 27 million combinations, they were going to do that over a 100-year period in 10-year increments. So once you kind of multiply that out, they were looking at a combination of 10 to the power of 74 scenarios, which is just not possible to run in a flood model. So our industry is really at the point where we can't do it alone when we start doing all those simulations, and we did look to a data science team to help us out on that.
Thanks, Sophia. It's a really interesting example. So before I throw it back to you as the audience for any thoughts on other areas that could be used to reduce the number of simulations, don't forget that limiting simulation numbers can be as simple as simulating only the events you really need. For example, simulating all durations up to 120 hours for a small catchment with no storage should not be your default. So over to you, audience. Are there any other critical considerations for defining the number of simulations?
So this one, we've talked about the difference between the Q&A line and the chat line. This is one you can put into the chat. This is not necessarily a technical question for the panelists to answer afterwards during the Q&A session. This is into the chat line. Just put in your audience input on any other considerations. If you think of something that you would have said, and it looks like from the chat so far, some of the presenter or some of the attendees could be presenting in this as well. Usually we don't necessarily call out you by name, but I will call out Jonathan Cleric here, who is a familiar face to some of the presenters here as well, who says 10 to the 9th or 10 to the 10th simulations. So if we're tracking the number of simulations from the audience attendee members, we would have to have a category. It went from 1,000 was our max. We could go 1,000 to 1,000,000, 1,000,000 to 1,000,000,000. Jonathan says he's gone between the billion and trillion simulations. So I don't think anybody else is going to beat that. So with that question up here, pop that into the chat line here. Chris, if you wanted to start sharing your screen and offer any other thoughts on what Sam has just shared with us, and then we'll continue to answer your questions in the background. So I can see your screen just fine there. It's going into full screen. So yeah, just if you want to follow up on anything that Sam mentioned, and then over to you.
Okay, thanks very much, Cray, and thanks, Sam. In the interest of time, I'll just skip straight into the TUFLOW slides. I'll be focusing on tips for reducing HPC simulation times. The main idea behind this being when you're running simulations on cloud hardware, you're paying for time. So it's very much in your interest to reduce the amount of time that you have to run the said simulations. I apologize for a second. I just have to move my Zoom, the notes. Okay. Let me minimize that. All right. So I'm focusing on 4 main talking points here. And I've come up with this list based on support inquiries that we've received, where we notice these are very common things where people could make slight changes to big effect in terms of making their models run faster. So the 4 topics are: consider your domain extent specification when you're building a model, review your model, your minimum time step in HPC, review your subgrid sampling parameters, and also choose an appropriate 2D cell size. For the purpose of this demonstration, so we can look at or talk about some real numbers, I've used a small example model. It's a flood simulation. It's roughly 50 kilometers squared, 7.5 kilometers by 7.5 kilometers. It uses a 20-meter cell size and a 24-hour event duration. Throughout the presentation, I will mention simulation times, and those times reflect the time it took to run on Flood Platform. Some of this content will be specific to TUFLOW, but the concepts are transferable to other software as well. So even though it'll be TUFLOW specific, you can use the concepts in other packages. Let's start with the domain extent review. when you first build your model, you should be trying to nest your computational domain as nicely around your project area or your total model area as possible. And if you don't, then you're really just allocating compute resources to other parts of your model where nothing's happening unnecessarily. In TUFLOW, I highly recommend after you build your first model to load your domain check file. There's the name of it down at the bottom of the white polygon there, dom check r. Load that file in and it'll bring up a polygon. That's the black dotted line that I have on the screen here surrounding my model area. If I revise the domain, and I'm doing this in this TUFLOW model via two specific commands that are in the geometry control file. There's the read GIS location line, which is the red arrow line there that defines the X axes of my domain. And then also I use the grid size command, which I've highlighted in blue there on the left. I've nested my domain quite nicely around this model area now. That one change reduced my simulation time from 57 minutes to 38. So it's a pretty significant reduction in simulation time. That should be your first step whenever you're building a model. Think about your computational domain. The next thing I would typically review once I have a working model is my minimum time step. Now, TUFLOW HPC includes a really great feature that enables it to calculate an appropriate computational time step to maintain a stable solution. Now, due to the fact that the software is selecting the time step for you, review of that time step becomes a really useful model health check parameter. In essence, a healthy model will be able to run and operate at a larger time step and will run simulations faster than an unhealthy model. Now, I've listed out the general steps in terms of what you need to go through to review your time step here. Step 1, enable the time step output. Step 2 would be to review your control number outputs, and they can either be viewed in a CSV file, which I've highlighted in blue there, or alternatively the flood platform QA plots. I would then review the computational time steps. So going back one more, talking about the control numbers, depending which control number dominates, that's the celerity number, current number, or diffusion number, that provides insight to me as to what sort of model features I should be investigating when I'm trying to fix potential issues. So then I'd look at my time step values to see if they're within the range I'd be expecting. And I review my model details to try and fix issues if I think there are any. And I'd repeat this process a number of times until I get to a point where I think the model is happy and healthy. This is a very big topic that I could talk about for about 30 or 40 minutes, which I'm not going to do here. So I've included a few links there. If you don't know much about this, I'd highly recommend downloading the PDF or watching the video after the fact and looking at those links, or alternatively, come to one of our training events and we'll talk you through this in a lot more detail. So I'll do it very quick here. So I've turned on my time step output and I'm looking at it here now, and I've colored the output from red through blue, with the smallest value being red and the highest value being blue. By then zooming in and inspecting the area that's red, I can find the location which is defining what the time step has to be for the entire model. So one time step is used for the whole model. It's that red area there that has a DT of 0.18 seconds that's defining what had to work for the entire simulation. With that information, I'll now look at my control numbers. The top graph I've plotted here is my control number data for celerity number, current number, and diffusion number. And the bottom graph is my computational time step. Let's look at the top graph first. In the top graph, we have the celerity number as purple, the current number is blue, and the diffusion number is green. Now, whichever one of these approaches its defined limit, which I've specified there as 1, 1, and 0.3, whichever one approaches that defined limit provides insight to me as to hydraulic behavior that influences why the model had to run at a certain time step. If celerity is the controlling number, then it relates to water depth. If current number is the controlling number, high flow velocity is typically the thing I'd be looking at. And if diffusion was the factor, then I'd be looking at my cell sizes. Perhaps I'm using a cell size that's too small. Now, in this case, it looks like the celerity number is the one that we're interested in, the purple. Let's just look at the time step first before we move on. For a HPC model that is celerity controlled, I'm expecting my time step to be about 1/20th of the cell size or greater. That's what I should be aiming for. So my model is a 20-meter cell size. I want to have a time step that's greater than 1 second, and I don't have that at the moment. So this is really not a very healthy model. Now, I'm looking at the flood depth result. In this result here, I'm zooming into the location where the minimum time step occurred, and I've inspected what the maximum flood depth is. And it turns out it's over 10,000 meters. There is no way that is real. Then we move to the detective work. Let's work out what is causing that input issue in our model. If I look at my digital elevation model, I can see that I'm missing some data. I'm missing an entire tile. That's an obvious issue. Once we replace that tile, we then look at our control numbers and time steps again, and this is how it changes. So all of a sudden, you can see our time step has gone up to around about 2 seconds, or it was 1.8 seconds. So it's gone up by a factor of 10. That's now reduced our simulation time from 38 minutes down to 5. That had a huge impact. Next on the list was subgrid sampling. Subgrid sampling is a really useful feature that enables the parameterization of 2D cell storage and conveyance geometry within a 2D cell. I've tried to convey that concept in the top right image there. If you don't know what subgrid sampling is, please put a comment in the Q&A, and I'll place a link to another video that can help you understand what it is. In the 2025 release version of TUFLOW, it will automatically adopt your digital elevation input resolution as the subgrid sample frequency. Now, if that frequency value is too great, there's two examples there on the right. So a smaller frequency number will have less sample points within a cell than a larger number. So if your DM resolution is so fine that the default sample frequency is, say, greater than 11, then I'd be recommending testing bringing down that sample frequency value. The way that you would check this is you go and look at your log file, just put in a search term for SGS sample frequency. You can see this example I've put here is stating a value of 31. I could literally just copy that command from the log file, put it into my next simulation to hardwire the sample frequency to a lesser value. I typically start with looking at 11. See how that impacts the results. If it doesn't change your results significantly, run with that. This one change here reduced my simulation time from 5 minutes down to 3.5, and the model now uses 20 times less RAM. That's of special significance because the less compute load you require will determine what sort of hardware you can use to run your simulations. You can typically choose cheaper hardware on the cloud if you require less RAM. Okay, the last talking point I have is 2D cell size selection. What is the correct 2D cell size? I've done, I think, 5 or 6 webinars now with AWS, and every single time someone has asked, can you please advise correct guidance on 2D cell size selection? Is it this resolution, this resolution? If you don't know, I'd recommend going back to the webinar I presented back in 2020. There's a 45-minute discussion that works through exactly or the steps you should take to choose the right cell size. I'll give a very quick example of the concept here, but if you need to know more, please go to that webinar. It'll be on the YouTube channel for AWS. Let's circle back to our project model, or the example model, and assume that we have a project site where I've written project site and I've placed a cross-section inspection line through the said site. I've run this model for a series of different cell resolutions from 60 meters down to 5 meters. And in the table on the left, you can see the simulation times associated with each of those resolution changes. And then on the right hand in this graph, you can see the water surface profile for the maximum water surface for each cell resolution. And you should notice that at a certain point, when I'm reducing the cell size, the results actually start to converge to a common solution. That's what I'm after when I'm deciding what cell size to choose. I want to choose a cell size where my choice does not influence the results. Rather, it's converged to a common solution. So with that key objective in mind, the 60-meter simulation, a resolution simulation is not appropriate, or is the 50, or is the 40, or is the green, the 30. I've color-coded those cross-out lines with what's in the graph there. But the 20, 10, and 5 all produce a similar result. I'd be happy using any of those. In terms of cloud computing, however, the 20 is the optimum choice. That model takes 3 minutes and 49 seconds to run, whereas the same model with equivalent results at a 10-meter resolution would take 20 minutes, and the 5-minute meter model would be 211 minutes. Small numbers for this example, but if you use that as a relative reference to your own simulations, like imagining a 20-meter model ran in, say, 2 hours, then multiplying that by 7 to go to a 10-meter resolution is a significant uplift. I suspected that someone might ask, well, how much did that simulation cost to run on Flood Platform? And the 3-minute simulation costs 12 cents. I should state that's just for the Jacobs Flood Platform hardware. It's not for TUFLOW software licensing. We've come to we've configured TUFLOW so that you can bring your own licenses into Flood Platform. If you have a TUFLOW cloud license, you can use it directly in there, or as of today, or any other cloud environment for that matter. So 12 cents. On that, I might actually pass back over to Sophia, who will introduce Flood Platform.
Excellent. While we're waiting for Sophia, if you want to share your screen as well, then again, just keep in mind that the most upvoted questions in the Q&A are the ones that we're going to handle with the expert presenters at the end as a panel discussion. And what tends to happen is that a lot of questions come in like 2 minutes, 5 minutes before the end of the session, and we won't necessarily have time to get to those if you wait until then. So do keep those questions coming along the way. I can see that screen is coming through just fine now. So Sophia, over to you.
It's great, and thanks, Chris. I think everything that Chris talked about is not just important inside a cloud environment. You've only got a set amount of machines that you can run simulations on, and you're often sharing that with the team. So definitely making sure that you're running things efficiently is important before you even move to cloud. So we did have a poll earlier about whether you've got experience using cloud, but let's dive a little bit deeper for I think there's 20% of the audience that have used cloud. So we could pop up the extra poll. If you have used cloud computing specifically for flood simulations, what's your experience? So if you are new to cloud and you don't really know what it is, please do click check the first option there so I can explain a little bit better. But just kind of understanding what experience people have had. And I've heard all sorts of stories. As soon as I mention cloud, some people are quite nervous and worried because they've had a poor experience. We want to kind of talk about that and when not you should use cloud. That's good. People have come to the right place asking what is cloud, which is good. So a lot of people haven't considered it. 15% have tried it, but it was too difficult to set up, which I totally understand if you don't have a platform like Flood Platform to help you do that. A few people have used it, but found it too slow or too expensive, and then some people are using it from time to time. And 0% are saying that it's all that we can use. So 2025, we're not there yet in the IT world.
Sophia, there's one question that came through from the audience here saying, we should have added an option for, I considered it, but I didn't follow through with it because of the costs. So you might want to address that briefly.
Okay, understand. All right, well, for the people that, asking what is cloud, essentially we're moving from, using your own laptops or machines in your office to renting what you need through the internet. So whether that's through Amazon or Azure, or Google, exactly how we are offloading the photo storage on our phones to cloud. We can do the same thing for the work that we're doing. So whether that is storing flood models and the data in the cloud, or whether that's offloading your simulations to hardware that's potentially better than what you've got for a shorter period of time. So some of the benefits of doing that is, the biggest benefit by far is the scalability. So often, I've never met a flood modeler who has said, I've got enough hardware, don't need any more, I'm good. So having the option to be able to scale up when you need it, particularly when your project deadlines are coming close. And if you're working in a team, the deadlines seem to always come at the same time for everyone. So having access to those resources quickly is great. There's also no upfront capital costs. So, if you're just starting out with flood modeling, for example, you don't have to go and buy a bank of 10 servers with high-end GPUs, which thousands of dollars. You can jump into the cloud and get started for dollars or cents, even if you're running some of the small simulations that Chris talked about. There's reduced IT management. So it's pretty common to have a bit of tension between IT departments and flood modeling teams, just because they don't have a common goal of what they're trying to achieve. We need more storage and more simulation power than anyone else in the business. You're not reliant on your power when you're doing your flood simulation. So back in the day when I was modeling for council, we had backup power supplies, because the last thing you want to do is run a simulation for 4 weeks and find that the power cuts out at 3 weeks and 6 days, and you lose everything. The last three there they're around cloud, but they're more specific to flood platform and what we're offering. So you do get automated backup of all the models that you're storing in the cloud in flood platform. And that's all free and automated. It does allow you to work in a collaborative environment, because anyone can kind of access it if you give them permission. And you can also access updates from anywhere. So working in a collaborative environment, if you're off on holidays, someone else can set off simulations for you and have a look what's going on. Or if you're a super nerd and on holiday, if you like to check what's happening back at the office, you can log in on your phone. You don't need to be in the office. You don't need to be on VPN. You can access it from anywhere. It's not all blue skies. When we're talking about cloud, there are some limitations. So, one of the biggest limitations, and it's associated around with cost as well, and people's kind of disappointment when they move to cloud, is cloud only offers commercial hardware. So the gaming cards that we are usually using in flood modeling, and this is in Australia, I reckon we are the highest users of gaming cards for purposes outside of gaming. But everyone's got, a couple of RTX cards. What a lot of people probably don't know is, one, they are not built to run consistently. They are built to run, for an hour or two at a time. We are not doing that. We're smashing them full time. And they're also not built to be energy efficient. So they require a lot of energy. And we do hear stories of things setting on fire because of the way that we're using them. So the last thing a commercial cloud provider wants to do is find that there's fires being set off in their server rooms. So that's why they only use commercial hardware. So you won't find, when you log on and you try and find an RTX card that you're trying to use to TUFLOW, they won't be available. It'll be something else. Obviously, it requires internet or the data transfer. You're reliant on third-party platforms. So you do see from time to time Amazon Web Services go down. Everyone's kind of life halts for an hour or two while they get that back up and running. So that does happen from now and then. And then there's also configuration overheads. So you would have seen the simulation times that Chris mentioned earlier, and trying to get the grid size so that it's not impacting on your results. So the first 4 simulations, I think, were under kind of a minute or two. But when you run them in the cloud, you'll actually find that the overhead of finding the hardware, setting up TUFLOW, setting up the model will take a minute or two. And so essentially all of those runs will take the same time anyway. So just understanding that and calculating that into what you're doing is important. So I talked quite a bit about commercial versus gaming cards, and this is a slide that just shows the difference between them. So the RTX 5090, if you're an Australian flood modeler, everyone is pretty up to date with what graphics cards are around. I think these came out pretty recently, and they're the hot one to get if you're doing flood modeling locally. And you can see there, based on the number of cells that are running and the simulation times, they are giving the best performance for a single simulation by quite a bit. And then we have the options that are available in the cloud that are commercial cards. So you've got the A100 that's very close to the RTX cards. So we get really good performance from those. Then we get the A10s, which are about in the middle there. And then we get the T4s, which are, people tell me they're quite old. They are. But there's lots of them in the cloud, and they are fantastic cards for continuous usage. So that's what it looks like on a graph. To give you a bit of an idea of the benchmarking against what we usually use for TUFLOW modelling in Australia, and this will be different. I've noticed that Australia's gotten right into GPU modelling, so we have a lot of cards, whereas other parts of the world perhaps don't have access to these cards as regular as the Aussies do. But this is a screenshot from the TUFLOW benchmarking results, and you can see there where the cloud hardware sits. So you've got the A100s pretty close to the top, but definitely not first. And then sadly, the T4s, which are what we're using in Flood Platform by default, are at the bottom there. But I will mention this is the high-end GPU result. So if we look at the full spectrum of GPUs that you can get, the T4s are actually sitting closer to the top. So you might be wondering, why do we use the T4s by default if they don't provide the best performance out of all the options that we have? And it's really about being cost effective. So the T4s, they're about 91 cents an hour, whereas the A100s is $7 an hour. So you can see over the simulation time, they might run faster, but they're so much more expensive that it ends up being a higher cost for that simulation. So you might do that if you've got a really tight project deadline, or perhaps you've worked out that you've got so many licenses and you need to run them in a certain amount of time. But it probably is more cost effective to actually rent a few additional TUFLOW licenses, put them into Flood Platform, and use the default T4s. Right, so that's all for a single simulation. It's not looking all that fantastic for the cloud. Why would I run a single simulation in the cloud if it's going to cost me more and it's going to be slower than what I can do on-prem? So cloud really isn't the best option if you're only running one or two simulations. The benefits really start to stack up when you run multiple simulations. You can see that in this graph. We've got the simulation time on the left axis. Down the bottom, we've got the number of simulations that we've been running. So this is actually something that I was doing yesterday, testing this all out, making sure that my numbers stacked up. So you can see there for one simulation, Flood Platform or the cloud is the darker blue. It's actually more time consuming to run one simulation on Flood Platform than it is locally. And that's using my laptop, which does have a very good GPU in it. Once you get to 2, it starts to level out. But what you see is the more simulations you run, the time that it takes to kind of return those results in Flood Platform stays really consistent. You do get a little bit of variation once you start getting higher numbers because we have to reach out to more regions to find all the resources. But essentially, it stays pretty flat. Whereas when you're running them on-prem, you really are limited to the hardware that you have, and you have to wait for one simulation to finish before you can start another. I'm aware it's not all about the GPU cards, and it's also some people can run multiple simulations on a GPU. So I have accounted for this. I've been running 2 at a time on my card, but it does slow everything down. Right. And just to kind of look at the overheads that we have with cloud, is why a single simulation costs or takes longer is just because of this resource allocation and the configuration. We also have to shut down the machine because the last thing you want to do is be paying for a cloud resource when you're not using it. So we only pay for when you use it, plus the little time up front and afterwards to start it up and to shut it down for you. Right. So we'll fly through this. This is an example of how you would do this inside Flood Platform. Right. So I will admit I've sped this up a little bit because no one wants to watch simulations run unless you're a super nerd and like to watch the TUFLOW matrix screen. But I've got a model here, which is the Queanbeyan demo model you might have seen in previous webinars. And what I've done is I've gone and applied some R&R ensemble rainfall to it. And we've created a loop batch file to run in TUFLOW. So you can see there that I've got 2 APs, different durations, and the 10 storm patterns. And what Flood Platform does is when you upload that to inside Flood Platform, it'll create all the simulations for you. I haven't uploaded any results because we're going to run them all inside the cloud. So you'll see there that you have the simulation names and some details about them, but you don't have any information on the results. So I'll just fly through the screen there. We've got all the simulations for the 10% AEP. So I've got 50 simulations there. I know that's probably not enough for today's environment where we're running all the different durations for all the AEPs. But what we can do there is really quickly pick 50 simulations off the list, which are all the 1%, and add them to the simulation queue. That's kind of your first step inside Flood Platform. You can go and add simulations from multiple projects. And then once you're happy, you can come into the simulation queue and set them off. So you can set one off at a time by selecting them in the list, or you can select them all, which I'll do in a second. You can also select the version of TUFLOW that you're running. So you don't have to go and install lots of different versions, and you can also run, upgrade a simulation to the latest version to see what happens. When you hit run, Flood Platform goes and checks one, have you got licenses to do what you want to do? And also, do you have all the data to run the models that you need to run? If that doesn't happen, or you're missing a tin file or a ground model, then it will stop you there before you start trying to pay for things. So you can see that this is all sped up. So I've skipped a little bit of the setup time, and we've got some simulations already running. But essentially what happens is Flood Platform will send out a message to the cloud to say, hey, someone wants to run 50 simulations. I've got 50 TUFLOW licenses. Let's go all in parallel. So you can see there all the simulations, the progress is actually all happening in parallel, really. And you can see there the running with warnings. That just means that there was some warnings at the start of the simulation from TUFLOW. It doesn't mean that there's warnings from the cloud. So you can quickly use that view to see how things are going. You can view this on your iPhone. And if you want to have a look at how that simulation health is tracking and make sure that you'd ultimately want to do this before you launch 50 sims, but you want to go and have a look how the simulation health is going. This is what Chris showed earlier. You can see the calculated time step. You want to make sure that that's okay. You can see the different control numbers as well. And I saw a question in the chat about this crashing Excel. So we'll have to do some testing on whether how many data points we can handle in Flood Platform. That hasn't happened to you yet. You can see that this is actually not the healthiest model. We've got a volume error of 13%. And I've also missed the peak of the flow, so you can see that wet cells are still climbing. Luckily, it's a demo model, and I'm not banking on my job of being a great TUFLOW modeler. So once you've finished your simulations, Flood Platform will tell you the simulation time and the cost. This is in pounds because I've used the UK Teams account. But that simulation costs about 25 cents. You can go straight to the results. So depending on what you want to do with it, if you are reliant on internet speeds, you can and you want to use that data for something else, you can download everything straight from Flood Platform. But if you don't need to download the data, you can save yourself some time and you can just view the results and share that information through the web. And that will save you quite a bit of time and money. So Flood Platform allows you to view all the results. You can click on the 1D elements and you can see the flows through the pipes and also the graph. You could go through the time steps and have a look what's happening in the model. And you could also click on any of the 2D elements. You can change the way things look inside Flood Platform. You can add comments. You can export screenshots. Lots of different options there inside Flood Platform. And one thing that I'm quite happy about is we've just provided some extra options on how we can view the velocity vectors. It was quite simple before. It's still, I mean, you've only got two color options, but you can do lots of different things there with the scale and the visibility of it. Just checking on the time, so I might pause there for a second with the demo. And I was going to share a case study of the Thames flood mapping project. So this is something that's about to kick off early next year, but we will be using Flood Platform and Cloud in entirety to run 250 flood simulations. So if you have been thinking, oh, Cloud looks okay, but I don't want to be the first to try it, don't worry, you won't be. We are going hard with the first one off the rank with a big project. Right, so I spoke quite fast there, Craig, but hopefully we've got a bit of time for questions.
Yeah, for that project there, 250,000 simulations, it said. If there's any background, that if you wanted to cover that in more detail, if there's any background information you can put up there, in the chat line for people to look up and get some more resources on that. I think everybody would be very interested in seeing that. But in the interest of time, if anybody does need to run on the hour, let's make sure we get a couple of questions answered. Do scan that little QR code if you're interested in giving this a shot yourself. So we'll bring our other presenters back on. Chris and Sam, if you want to turn your cameras on. And thanks for all the presenters and for putting those awesome slides together. Sophia, kudos for doing a live demo. You just never know how those things might work on the fly, and it looks like that you did that very confidently. So thanks for walking us through a live demo there. Maybe if we just kind of go back through the presenters in the order that we had them. A lot of questions have been answered in the background. Maybe we'll start with Sam. Is there anything that you wanted to point out to the audience with the understanding that those watching the YouTube recording won't see this chat that's in the background? We will try to post the transcript of the chat that you can link to at the bottom of the YouTube recording in the description. But maybe just reiterate anything that you've covered in the chat line and any questions that you think you might want to hit for the audience.
To be honest, I think all the questions are directed at technical TUFLOW questions or technical flood platforms. So obviously I was very articulate.
Yeah, and maybe we'll pass that on to Chris then. But you did answer the one question, which was, people were asking about the cell size there. Our Australian Water School webinars are numbered. It makes them easier to find. And so the one that Chris did about 5 years ago was number 99, just before we passed the 100 threshold. Now we're well into the 200s with these ones now. So that was back in the pre-COVID days, I think, that we did that presentation. So go have a look at that link. We'll link to that in the description as well. Thanks for that, Sam. But Chris, you've answered a ton of these questions technically about TUFLOW. Any that you wanted to hit in particular?
I'd like to actually bring together one question, also something that's in the chat. So someone basically asked, look, I really can't see the benefit of using the cloud over my own machine. And then someone in the chat has also said, look back at the envelope calcs, the cloud cost per hour aggregate, more than 38 cents per hour becomes more expensive than on-prem. So what use case aligns itself well with the cloud? I'd say whenever you need to upscale because you're exceeding your own in-house compute ability. And I can use the Brisbane River flood study as an example of that. We didn't use the cloud with that one, but at that point in time, we used something called HT Condor to basically link up 20 different machines to run all of those 1D simulations. Today, we probably wouldn't go through that pain, and we just spin up virtual machines on the cloud and distribute them across 20, 30, 40 virtual machines there without compromising the computability of others in the organization. So I think whenever you need to upscale to meet your project needs, that's where it's really useful.
Excellent. Thanks for that. I don't know if Sophia, if you've had a chance to scroll through any of the ones that came in during your presentation. Again, want to make sure that we've hit the most upvoted ones before we get to time. We might run a couple of minutes over, which is fine as well. If you do need to run, you'll get a link to the recording. Any of those that you wanted to hit in terms of the ones that have been most upvoted, Sophia?
Yeah. So someone's asked, or John's asked about running on simulations and whether we reserve the cloud resources for you. So we do. There is an option to kind of they're called hot instances, where if you want to run the risk, it's a lot cheaper to run on a hardware that if someone else wants it and is willing to pay for it, you get a 2-minute warning and you have to close everything down and it's gone. So If we can get that to work and we can get everything to shut down in 2 minutes successfully and pick up another resource quickly, that's something that we would do. But at the moment, we are reserving everything when you need it. So.
Okay. Well, we're talking about water here, and sometimes I've had the experience of trying to fill up a pool or leaving a sprinkler on or something, or some leak. You go back to the water corporation here and say, sorry, I went on holiday and my water was still running. Anytime if somebody's inadvertently still running something, have you had chance, occasions, I think Chris mentioned a couple of these this morning to me, that some people have just left things running. Is there some sort of stopgap that says, hang on a second, you're not actually doing anything, you're just logged on here? Does that happen?
So actually with HPC, we can see that happening. So obviously if your simulation's finished, it'll close down and you won't be charged. It does that automatically. But what you can find is people with HPC, if they don't do the steps that Chris talked about and they don't have a healthy model, it can run, much, much longer than you think. And we can see things running for kind of weeks instead of days. In that case, we have seen it and we've contacted the people and asked, do you want us to shut this down?
No, that's great. Wondered if there's some sort of stopgap. I think, Chris, you mentioned the one that had just been running for like 4 months straight.
Yeah, for 3 months. That wasn't on Flood Platform. That was on Azure. But that was an interesting little surprise when the bill came through.
Yes, absolutely. So yeah, we'll probably go around the room one more time and just see if there's any other, final closing remarks that you wanted to make. Thanks to everybody who's kept this interactive and has put some of these questions into the chat line. I mean, this is where we're at now. You don't just run one example and say that's the result. You run a bunch and you kind of see where the bell curve kind of takes you into the middle. And we do this with dam breach a whole lot. The Australian Water School has some courses that use McBreach for a dam breach. The MC in the McBreach is not for Macca's here, but it's the Monte Carlo, where you just run endless simulations because you really don't know a lot of these variables. And so sometimes you just have to run these things thousands of times and you have to keep it very efficient. If you want to Google setting up and running a Monte Carlo model in 2 minutes, try Googling that one. I did a demo of one. It's a bit of a gimmick, and looks like Google's AI has picked up on that. But that's a little fun trick for you. There is a model in the background that you can run and set it up. It's a Monte Carlo model that you run in 2 minutes flat. With that, again, a couple of things then that we wanted to mention in the background. If you want to try this on your own, do fill out the poll questions. What we always have in the background on the poll question when you leave is whether you'd be looking for more training in this. Do you want to see some actual training in this? Do you want to, give it a start with your own? Do you want to try this on your own? Do you want to be guided through this by some of these expert presenters? If so, 2026 is, starting to stack up in the beginning of the year, but the rest of the year is wide open right now. We're open to your suggestions. Do let us know. So fill out that feedback survey at the end, and let us know if there's some of this material that you want to see more of. So let's go back around the room, have some closing remarks from everybody. Any take-home messages that you wanted to say? You could reiterate one of the questions that has come in from the audience if you'd like. But let's go back to Sam, and then Chris, and then have Sophia wrap it up for us. Over to you, Sam.
There's a question there about, do you need to do anything special with your model to be able to run it in the cloud? And I'd say set it up well and think about it, what you're trying to solve as you set it up, and nothing special, just needs to be a good, well thought out model.
Yeah. Get some of those glitches worked out first. Don't upload it and have it running in the cloud and then find your errors. Get it nice and smooth and working first, and then transfer it over. Chris, you agree with that?
That's a really valid point. Do all of your model build activities on your own computer, and then once you're to a point where you're rolling out all those scenarios and simulations, pass up to the cloud then.
Yeah. Sounds good. Any other questions you wanted to hit, Chris, before we let Sophia bring it home?
Look, I'll pass over to Sophia. I think, yeah.
All right. Take home messages, Sophia.
Just kind of reiterating the sequence that we did this presentation in is, when you're running simulations, make sure you're not running anything that you don't need to be doing. Make sure your model's nice and healthy. And then if you need more resources, hit up the cloud and give it a try. Closing remarks, I guess. If you're interested in Flood Platform, do feel free to reach out and try that free trial. But I'm also running a 2-hour free training session next week on Wednesday, where we'll go through all the steps and how to kind of set up a model if you're interested.
Perfect. Well, we'll provide those links to you. Maybe we'll put those in the YouTube description as well. If that'll be recorded, then hopefully people can watch that later on as well. So from the poll results in the beginning, 20% attended this webinar on cloud computing, not having ever used cloud computing. So I assume that the 80% of the attendees who have not used it intend to use it at some point or want to see whether it's going to be worth using. And so I would hope then if we have the same poll a year from now with the same group of people, maybe that percentage would have gone up. So thanks for the Australian Water School staff for in the background for running the polls for us and for all of the administrative support that we've got for these webinars. It's a pleasure to bring these to you for the industry, and it's a pleasure to interact with all of the attendees out there, trying to do their best to model floods. And with that, we're closing up with the Australian Water School. I did the last webinar from over in a blizzard over in Canada and back into the heat here. And we've got AC/DC coming right down the road today, and I'll be at that concert tonight. So Australia rocks. So great to be with you from the Australian Water School. Thanks for all of the support that we've got, and keep those questions coming. Keep this interactive. Connect with us on LinkedIn, and keep this an interactive community where we can help make the world a better place and a safer place in the event of some floods. So with that, we'll see you again next time with the Australian Water School. Bye-bye.